Hello, this is Mr. P, and today we're going to learn about functions. At the top here we have our official definition of a function. Function, and we're going to call the function f. Function f from set A to set B is a relation, and that's a very important word there, I'm going to underline it, a relation that assigns to each element in x, or each element, sorry, x in set A, exactly one element y in set B. And that's very important, exactly one. The set A is the domain, or the set of all possible inputs of function f, and the set B contains the range, which is the set of all possible outputs. So the official definition can be restated a little more simply. It's basically a relationship between two variables. One of your variables will be the independent variable, which will be your input, so it belongs to in the domain, and the other variable will be the dependent variable, which will be the output. Now, there are some characteristics that must happen in order to call a relation a function. And we can use the time of the day and the temperature as a good example to go through these characteristics. So first of all, each element of A must be matched with an element of B. So in our example, to compare everything to reality, at some time during the day, there is going to be a temperature for that time. So at 1 o'clock, for example, it is 9 degrees Celsius. So for everything in A must be mapped to something in the range. Now, some elements of B may not be matched with any element of A. That's okay. That doesn't conflict with reality, because if you look at 5 degrees, for example, at no time during this day was it 5 degrees. Yet it would be a possible temperature for other days, maybe. So the fact that not every one in B is matched with an element of A, that's okay. That does not break reality. Third one is two or more elements of A may be matched with the same element of B, and that is fine. Take, for example, at 3 o'clock it was 15 degrees, and at 4 o'clock it was also 15 degrees. That's okay. That does not break reality. But what does cause it not to be a function is this last one here. An element of A, which is the domain, cannot be matched with two different elements in B. And this is where we have that exactly one idea. In other words, at 3 o'clock, I can't say at 3 o'clock it's 15 degrees and it's 12 degrees. That would not be realistic. That would not work. So if you want to think of time of day and temperature to keep your head straight on these rules, then you can do that as well. All right, let's look at some terminology, of course, for functions. And here's another definition of function, because you're going to see many different definitions depending on the textbook author or the professor. But this one does talk about the independent variable and the dependent variable. The independent variable is your input, and the dependent variable is your output, because the value of the dependent variable depends upon what number you input into the function. And you can think of the function as a function machine. You input a number, you do some algebraic rules to it, and then you get your output. As far as notation, we have that y equals f of x. These are equivalent. Y or f of x is the same way to express the idea. For example, if I have the equation y equals 3x plus 2, this is a linear polynomial. You should recognize that as the equation of a line. It's in y equals mx plus b format. But we could also write this in function notation, saying f of x equals 3x plus 2. So both of these would be equivalent if we're treating this as a function. F would be the name of the function. X would be the independent variable, because that's the one you're inputting, f of x. And when you input the x and calculate or simplify and get a single value, then that would be the value of y, which is the dependent variable. Value of y depends on what you plug in for x. And we could also say that f of x is the value of the function at x, is another way to interpret that. So if you wanted to find some values, or you wanted to plot this, one thing you can do is make a table of values. And you can think of functions as little if-then statements. In other words, if x is 0, then I would substitute 0 in for x. 3 times 0 is 0, plus 2 is 2, so y would be 2. This gives us an ordered pair that we can plot, and that point would be on the graph of this function. Likewise, if x was 1, then 3 times 1 is 3, plus 2 is 5, so the ordered pair 1, 5. And if you remember lines, 2 points define a line, so once you have these 2 points, you could draw a line through them, and you'd have the complete graph of this function. Now, domains. The domain of the function is the set of all input values for that independent variable. And you're going to start to get into situations where you can have a domain that isn't defined everywhere. Now, for a polynomial, one great thing about polynomials, why we like working with polynomials, is polynomials, their domains are the set of all real numbers. Or in other words, we would say all reals is a short way to say that, but all real numbers would be the domain of a polynomial. And in interval notation, that would be from negative infinity to positive infinity, is how you would express that domain in interval notation. Now, if a value of x is in the domain, then it is said to be defined at that x. And if x is not in the domain, then f is said to be undefined at x. Now, as far as you're concerned for now, there are two things that are going to cause restrictions in the domain. Either you're going to have division by 0, or you're going to have taken the square root of a negative number. Now, there are others, like taking the logarithm of a negative number, and we'll get to those later, but for right now, all you have to worry about are those two problems. If you don't have those two problems, then your domain's going to be all reals for now. Now, if we look at the range of the function is the set of all possible output values. And in our example here, let's use the graph of y equals the absolute value of x, so that, or if we think of this function, no matter what number I substitute in for x, my result is never going to be negative. It could be 0, but it's never going to be negative. So my interval is going to start with 0, and then represent all possible numbers going up. So it's going to go from 0 to infinity. It's going to include the 0, because the absolute value of 0 is 0. But it's not going to include the infinity, because you can never include infinity. So it would be the interval from 0 to infinity, including the lower bound. Notice how this is very different than the open interval from 0 to infinity, which does not include the left bound, or the lower bound. Now, in both this function and our example here, in both of these functions, they did have an implied domain. Sometimes a domain will be explicitly given to you, but more often than not, you're just given the equation or the rule for the function, and you have to imply the domain from that. And like I said, for now, you're just looking for division by 0 or square root of a negative number. And we'll add to this list later on. All right, so let's look at some of the skills we need. First one is a pretty easy one. We're just going to test to see if an equation is a function. So we want to make sure that the equation represents y as a function of x. That means that it's going to be f of x, so x is going to be your independent variable, y is going to be your dependent variable. Therefore, to find out whether we have a function, we're simply going to solve the equation for the dependent variable. So for a, that's going to be, we want to get y all by itself, so we subtract x squared from both sides. That gives us y equals 1 minus x squared. Once we have it solved for the dependent variable, then we sort of use a little bit of logic and ask ourselves, if I put any number in for x, am I going to get only one result for y? And this is a polynomial equation, so yes, we're going to have no problems here. Any number I choose to plug in for x You're going to square it, subtract that from 1, and that will give you a single number. So therefore, yes, this is a function. With b, if we look at b, then again, we want to solve it for y, because we want to know, is it y a function of x? So to solve for y, I'm going to add x to both sides, which gives me y squared equals x plus 1. Then I'm going to take the square root of both sides. And when I do that, I'll have square root of y squared is y, square root of x plus 1 is square root of x plus 1. But now you must remember the algebraic rule that if you take the square root of both sides of an equation, you must add the plus minus. This helps us keep it the equivalency, because the square root of y squared technically isn't y, it's the absolute value of y. So to not have to write the absolute value signs, you can use the rule that if you take the square root of both sides, then you must add the plus minus. So now, with a little bit of logic, if we plug in a number for x, then we're going to get plus or minus some number. And that means y could be two possible values, which makes it not a function. So b would be no, it is not a function. All right, evaluating a function is very simple, but I'm going to give you some good habits to build. The first habit is always use the parentheses when you substitute in a value. Plugging in a number, always use the parentheses. So if we look at a and we want g of 2 is how we read this. In other words, what is the value of the function when the input is 2, the input is x? So you simply replace every x in the equation with a 2. But when you do that, you want to make sure that you use your parentheses. That way you don't change the order of operations. So here you have you have an exponent, and you have a negative sign in front. The negative sign is really multiplication. Negative sign means negative 1 times. So of exponent and multiplication, exponent is the higher order of operation. So that means g of 2 is really a negative 4, because you square the 2, 2 squared is 4, and then take the negative of it, which gives you negative 4. This does not mean negative 2 times negative 2. If the negative sign was inside the parenthesis, then it would be negative 2 times negative 2. And then, of course, 4 times 2 is 8, and then you bring down your plus 1, combine your like terms, and you get g of 2 is equal to 5. So that's our fully simplified answer. All right, for the next one, we have g of t, which is just a change in variables. But again, you should get into the habit of any time you substitute, use the parentheses. So it's negative t quantity squared plus 4t plus 1. So g of t is, notice we square it first, then we make it negative. So it's negative t squared plus 4t plus 1. That can't be simplified anymore because you can't combine any like terms. All right, the last one is where our parentheses really pay off. And again, we're taking our function, and everywhere there's an x, we're going to replace it with an x plus 2. So it's negative, and then in parentheses, x plus 2 quantity squared plus 4 times the quantity x plus 2 plus 1. And that means that g of x plus 2 is, now again, we want to square it first, and the square of x plus 2 is not x squared plus 4. Make sure that you're squaring the binomials properly. There is going to be a middle term, so the correct way to square x plus 2 would be x squared plus 4x plus 4. Some of you might call it FOIL, but make sure you don't drop that middle term. So we square it, which gives us this whole quantity, and don't forget, we're taking the negative of all of that. So it's still negative of all of that, and then we can distribute on the next one. 4 times x is 4x, 4 times 2 is 8, and then bring down the plus 1. That gives us g of x plus 2 is, now we want to distribute the negative sign, so it's negative x squared. This becomes a negative 4x, and then this becomes a negative 4. And we just bring down the rest of the problem, 4x, 8, and 1. So therefore, we want to combine like terms, and we do want to write our answer. This is going to be a polynomial, so we want to write it in descending order. So a quick scan of the exponents means my highest exponent is the squared term. There's no other squares to combine us with, so we just bring down the negative x squared. Linear terms, I have two of them, but you'll notice that they cancel each other out. So we have no linear term. And then what's left is just all constants, negative 4, positive 8, and positive 1. When we add them together, or combine them, then you get a positive 5. And that would be our answer. All right, piecewise functions. Let's talk about piecewise functions. It is possible to have more than one rule for your function. Different intervals can have different rules. That's called a piecewise function. So looking at this, if x is less than 0, we use this rule for the function. If x is greater than or equal to 0, we're going to use this rule. So the question here is evaluate the function when x equals -1 and when x equals 0. The easiest way to do these, so if we want x of -1, then you take your input and you first look at your intervals. Which interval contains this input? So -1 is less than 0, so it would correspond to this rule. So this is the rule that we substitute the -1 in. And remember, always use a parenthesis when you substitute in, because now we can see it. This one is -1 times -1, which is a positive 1 plus 1 is 2. So f of -1 is 2. If we substitute in 0 for x, then 0 is in this interval because it's or equal to 0, greater than or equal to. So I use this rule to substitute. So f of 0 is going to be 0 minus 1, which of course is just -1. And we're done with those. So just make sure you check your intervals to see which is the appropriate rule to use on a piecewise function. All right, next we have the domain of a function. And these can get a little tricky. That's why we're going to take these slowly. The first one, they're saying that f, our function f, is defined to be the set of, the braces mean the set of, these 5 ordered pairs. And remember, the ordered pairs is x comma y is how we normally think of the ordered pairs, but it's also input comma output. So the x's belong in the domain and the output and the y's belong in the range. So if we want to know the domain, it would simply be each of the inputs of these five ordered pairs. So our domain is going to be the set of -3, -1, 0, 2, and 4. Because remember, the domain is the set of all possible inputs. Well, these are all of the possible inputs, those 5 of them. All right, for the next one, we should recognize this as a polynomial. And we like working with polynomials. They're very easy to work with because right off the bat, we know that the domain for polynomials are all real numbers. No matter what we plug, no matter what real value we plug in for x, you're going to get a single real value as an output. So therefore, we can call them all reals, or we can use the interval notation from -infinity to +infinity. Now the next one does have a potential problem. It does have a potential domain restriction because we see a variable in a denominator. So if, for example, x was -5, well, -5 plus 5 would be 0, then we would have division by 0, which would cause a problem. So any other number will give us a value. Any other number won't be a problem except when x is -5. So 2 ways we can express this. We can use set builder notation to say that our domain is the set of all x such that, there we go, such that x does not equal -5. So any number is good except for -5. And usually when figuring out the implied domain of equations, it's usually easiest to see where the domain can't be, what the domain can't be, what number can't be in the domain, and then it's all numbers except the ones that cause problems. Now another way to write this domain would be, it would be the interval from -infinity to -5, union with the interval from -5 to infinity. So this is basically negative infinity to positive infinity, but not including the -5. Notice how the parenthesis here and the parenthesis here means -5 is not included in either of those two intervals. So as a whole, this would be every number except -5. All right, next one is volume of a sphere is V equals 4/3 pi r cubed. Now the r is going to be our input and the v is going to be our output. So the domain is going to be dealing with the r. Now you might be tempted to look at this and say, well, that's just a polynomial, so it's going to be all real numbers. However, you do have to be careful when your value or when your variable has a physical meaning to it or has a geometric interpretation. Here, r represents the radius of this sphere. And in order to preserve reality, notice how with b, for example, the x was arbitrary or it wasn't set up with some sort of physical reality. It was just x. So if your r is like a radius or something physical, then you have to realize that, well, the radius can't be 0 because then you don't have a sphere, and your radius can't be negative because that wouldn't make sense. The radius is the distance from the center to the edge in the sphere. So it's going to really be the set of all r such that r is greater than 0. I say greater than because even a 0 radius doesn't make sense. Whereas, we're going from the abstract function of b to a non-abstract function in D. So that can be a little tricky. Make sure that if you're using real values or have something attached to reality, make sure you realize those restrictions. All right, and the last one is a square root value, which should be that red flag. Anytime you see a variable in the denominator, that's a red flag that you may have a domain restriction, or anytime you see a radical sign with a variable underneath a radical sign, you may have a domain restriction as well. So here, the value underneath the radical sign, the 4 minus 3x, that is called the radicand. And the radicand must be non-negative. In other words, it can't be negative. It must be either 0 or greater than 0. So non-negative means greater than or equal to 0. And you have to really choose your words carefully. It would be wrong to say the radicand must be positive because it could also be 0. The square root of 0 is 0. So this is how we set up to try to find our domain. So our radicand, which is 4 minus 3x, that must be greater than 0, and we simply solve the inequality. Subtract 4 from each side, and then divide each side by -3. Remember that when you divide by a negative, you reverse the direction of the inequality. So x ends up being less than or equal to 4/3. So once you have your inequality, now we can say that our function is the set of all x such that x is less than or equal to 4/3. All right, let's look at one final example. It's going to be a nice little word problem. And it says a baseball is hit at a point 3 feet above the ground at a velocity of 100 feet per second and at an angle of 45 degrees. The path of the baseball is given by the function f of x equals this equation. Notice that this is a second degree polynomial, so the graph of this would be a parabola, as we would expect in projectile motion. And it says x and f of x are measured in feet. And the question is, will the baseball clear a 10-foot fence located 300 feet from home plate? And they want us to solve it algebraically and graphically. All right, so if we look at, just make a visual representation of the problem, then we basically have in our xy plane here, we have x is going to represent how far down the field, and f of x, or the y value, will be the height of the baseball, how far off the ground it is. So here the function does represent the height of the ball, and when you trace that out, that will show the flight path of the ball. Now notice that it does start a little above 0 because we're starting at 3 feet above the ground. And then this now boils down to the question of, at 300 feet from home plate, in other words, when x is 300, what's the height? If that height is greater than 10, then we have a home run. If it's less than 10, then we don't have a home run. So we basically want to know what is f of 300. So all this problem is really just one of those plug and chug problems. So we're going to take the equation here, and everywhere that we have an x, we're going to substitute it with 300. So we substitute there and we substitute there. You can even put that in the calculator, and you'll find out that f of 300 comes out to be exactly 15. So will the ball clear a 10-foot fence? Yes, it will. Now that was the algebraic way to do it. Let's look at how we would do it graphically, in other words, on the graphing calculator, because we need to get very good at using our graphing calculators. So let me pull up our graphing calculator, which is going to be a TI-84. And as soon as that comes up, okay. So we have, whenever you first use your graphing calculator, especially if you're borrowing one in class, you should always go and check your mode first. Now for this particular problem, we want to make sure we are in function mode. And basically we want everything on the left to be checked. Don't worry about the clock, just everything else on the left should be checked. And if we're in the proper mode, that's good. Second quit brings you to your home screen if you want. But what we really want is to graph this equation, or actually this equation here with the x's. So we're going to go to y equals, and then we're going to put in our function, which was negative 0.0032 x. This is the button for x, and that x is going to be squared, or I could go to the second power if I want to as well. So it's negative 0.0032 x squared plus x itself, so plus x, and then plus 3. Alright, so our function is in the calculator, and now we need to set a window for the function. And let's first start us out with the standard window. So ignore that part for just a second. And then, now this would be your standard windows, negative 10 to 10 and negative 10 to 10 on both the x and the y. For our x values, we want to think about what values make sense here. So home plate would be 0 feet from home plate, and 300, what we care about, would be at 300. So 0 to 300 is what we care about for the x. But I do like to add a little bit on the left and right, so let's go from negative 10, so we can keep the first negative 10, and let's go to 310. That way everything we care about we know will be in the window. We're not trying to look at the edge of a window. And once you input the x values, there's a great feature for the calculator can calculate the y values for your window automatically in order to capture all of the data points, or all of the points on the graph. And to do that, you're going to go to zoom. This is after you've set your x values. You go to zoom, and it's actually choice 0, which is zoom fit. That'll fit the window to capture all of the y values. So you can arrow down and hit enter, or you can just hit 0 to go directly to it. And there is our graph. It is a nice parabola like we expected. Notice how there's a negative sign in front of the parabola, so it does open downward, just like we expected. And once we have this graph, we can go ahead and use our trace feature to find any values on the graph. So if you hit trace, once you have your graph, notice how, a little tough to see, but the cursor is actually blinking behind the equation. They give you the equation, and the cursor is blinking. We can arrow left and right and move the cursor along the graph. Or, an easier way is when you're in the graph and you're in trace mode, you can just start inputting a number. Any number you input, it takes it as the input. It'll take it as an x value, and then it'll jump to that point on the graph. So if I want to know what happens at 300, I simply hit 300, And see how it takes it as an x value. When I hit enter, it jumps to that point on the graph. Here's the point, 300. So when x is 300, y is 15. There's our value. And this works. This is great if you need to know multiple places. If I want to know what happens 100 feet away from the plate, I can hit enter, and 100 feet away from the plate, that ball is 71 feet in the air. So answering multiple questions is very easy with the calculator. Also, one other thing I want to mention about the calculator is when you use the zoom fit, although it puts all the data in there, you're going to have a different scale for your x and your y. As a matter of fact, even if you have the same scale, this is not necessarily a realistic view of the flight path. If you wanted a realistic view, then once you've done zoom fit and you have all the data in a window, then you want to do zoom square, which will be number 5. And that squares up your window so it's in this 3:2 ratio that the window is actually in. It's roughly 3:2, the dimensions of the window. And that is a more realistic flight path. That's what the ball realistically looks like as it goes through the air. So just be aware is going to become a little more important when you're more concerned about slopes at certain points in calculus. So zoom square will give you a realistic view of the graph. All right, so as a quick recap, in our calculator, we first enter our equation into the y equals, and then we set our window. We did -10 to 310. And then rather than set the y's ourselves, we did zoom fit. And when we did that, we got a graph that we can trace, input 300 for our x, and it jumped to our answer there. So will the ball clear the 10-foot fence? Yes, it will clear the 10-foot fence. And we're done.